Hello and welcome, everyone. Thank you guys so much for tuning in to another fantastic evening of virtual Café Sci. My name is Colin Summerhauser, and I'm the head of Haunted House in Palo Alto. And over the course of the last few months, many of you have witnessed the transformation of Café Sci from an in-person event to a virtual experience. And it's amazing to see how far we have come since our very first session. And because I know many of you are loyal returning viewers every month, I just wanted to encourage all of you to expand your horizons and check out our other events that we host as well. We host free virtual events every single week focused on a variety of different topics, ranging from technology to design and more. Head over to hauntedhouse.com/events for the full lineup and for registration details. And with that, remember to use the interactive question widget on the bottom of your screen to ask questions throughout the presentation tonight, and be sure to upvote the questions that you would like to see answered. And now I'll hand it over to our Café Sci lead, Kay, to introduce our amazing speaker today.
Welcome to you all from Café Scientifique, Silicon Valley. Next month, on the third Thursday of October 15th, we hope to have Dr. Mickey Sodi of NASA tell us about International Space Station, ISS, and how it is benefiting us. It will be the last talk of the year. After the holiday hiatus, we'll meet again in January 2021. But today I'm so excited to introduce our speaker, Professor Ilan Kroo. He is a professor of aeronautics and astronautics at Stanford. As a child growing up in rural Oregon in 1960s, Ilan was obsessed with flying. Along with his friends, he built a hang glider from bamboo poles, duct tape, and plastic. They took the contraption to a nearby dairy farm, ran down a hill, and would actually get a few feet off the ground before crashing. Dr. Kroo received his BS in physics and his PhD in aeronautics from Stanford University. He worked in Advanced Aerodynamic Concepts branch at NASA for 4 years before returning to Stanford as a member of the faculty. Professor Kroo's research in aerodynamics includes the study of innovative airplane concepts. As an early hang glider pilot, he was one of the developers of Swift, a high-performance foot-launched sailplane. Swift, weighing only about 100 pounds, could take off and land like a hang glider, yet maintain exceptional performance at high speeds. I do not want to bore you with his long list of publications, professional activities, and awards, but I do want to mention that he's also the founder of Z Aero, now Kitty Hawk Corporation, a company funded by Google's Larry Page with the mission to develop a battery-powered vertical takeoff and landing aircraft, which may be described as a flying car. Here is Professor Kroo.
I'm Ilan Kroo. Welcome to the Café Scientifique. I teach classes on airplane design and aerodynamics at Stanford. And I believe you see here a picture on the right side of the slide, taken from the 4th floor of the William Durand building at Stanford, looking down on the patio where a number of students are gathered to look at some of the autonomous airplanes that my students and I built of strange geometry, but they were very successful. The title of my talk is Air Transportation Redux. I had to make an asterisk there because many people don't know what redux means unless they went to the Matrix something movie. But it means brought back or revived. And it seemed very appropriate for the situation with commercial aircraft these days. So I'm going to be talking about several aspects of air transportation. And here's a quick outline, basically 3 areas. I'm going to talk, first of all, I'm going to talk a little bit about the big picture of air transportation, but then I will start talking about some of the crises that the air transport industry is facing now. I'll move from that to talk about sustainable aviation and the role of aviation on the environment and how it is we focus on sustainability in air transportation. Finally, I'll talk about some new ideas for reinventing air transportation and new concepts for airplanes and propulsion systems. So, well, flight and the idea of air transportation has inspired people for ages, from Icarus and Daedalus to children and people of my age all around the world. And one of those people was William Henson, who in 1943 decided that he was going to build an airline and an airplane company. And so what you see on this slide is a picture of a tea towel that he used for marketing purposes to try to raise money for this startup a long time ago. Don't read the text on the left. I'll read you the important things there. But as you can see, it actually preceded many of the inventions that came much later. So he patented this aerial steam carriage in 1843 and worked with John Stringfellow and Frederick Marriott. Marriott, after Henson stopped working on the actual airplane, he continued working on flying machines while becoming a well-known publisher in San Francisco. So it has a local flavor here too, this history. He built several models, some as long as 28 feet. They were partially buoyant, one of them called the Avatar. And if you want to see a model of the Avatar, when it's possible to do this, if you go to the Hiller Museum, right off of 101 near San Carlos Airport, you can see quite a bit more history on this very early airplane concept. He also built a triplane that he named after Leland Stanford in the 1870s, popularizing the idea of aviation long before it became feasible. I'll read you this one quote, which is from twainquotes.com, which shows just the extent of enthusiasm for this sort of thing. A reporter from Nevada with a noticeable drawl and a large red mustache often accompanied Mr. Marriott down to the basement of the building where he was working on the Avatar. The reporter was astounded by the stamina and enthusiasm of the editor as he worked hour after hour with only the light of a row of candles stuck in beer bottles. The reporter was the young Mark Twain. So this area has quite an interesting history connected with the early history of aviation. And yes, that Marriott is from the Marriott family who founded the hotels. So we spend a lot of time with transportation, and this is a plot of the number of minutes spent versus the year. And as among other things, you can see that people in California spend more than an hour and a half traveling per day. And despite the fact that aviation has been around and going faster and faster on the horizontal axis, we still spend a lot of time traveling, whether it's by air or car, or whatever. So it's important to, even those of us who are not working in the field of transportation, if we look how we're getting around, this is the same kind of plot, but it goes from 1880 to 2000 something. And on the vertical axis is the number of miles traveled per day, per capita. So it's the range that people travel. And you can see there are different modes of transportation. The highest lines are cars and buses and motorcycles with a linear fit there. There's walking underneath that. There are trains, which have been actually decreasing since 1900, as has walking. Air travel has been going up since 1940 or so, and looks like it's going up to at least the year 2000, while horses got down to a very small range by the 1920s. So we are well past peak horse, but we're not on this plot past peak air. So air travel is, of course, very important to many, many people. But it's interesting to look at how it's developed. This is not going to be a long history, but here is a picture of a 707 on the upper left of this slide. It was first flown around 1957. And to the lower right, you see an Airbus A340, which is still flying from time to time out of San Francisco Airport. And it first started flying in 1993, but it is a mainstay of several airlines still. The interesting thing about this is that if you ask someone at San Francisco which was a 707 and which was an A340, it would be really, they would probably not know. They're very similar, and it gives people reasonably the impression that, gee, not much has changed in 35, 40 years. And to some extent, that's true. The airplanes look like they did a very long time ago. Well, not only do they look like they did a long time ago, but their performance is not terribly different. So this is a plot which on the horizontal axis is the year that the airplane entered service. And on the vertical axis is a measure of performance. Whoops, I have to stop touching the mouse. The measure of performance here is the Mach number, which is really the speed divided by the speed of sound. So it's proportional to the speed, times the ratio of the maximum lift to drag. So the ratio of lift to drag, and especially when it's multiplied by Mach number, is usually used as a metric of aerodynamic performance, although people would argue whether that should be the case. So these are for large commercial airplanes. You see the 707 on the left being just under 15 on this scale. A 747 is about 15. There's a DC-10 down a little bit less than 15. An MD-11 on the right in 1989 or so, which was a variant of the DC-10, up at 15 again. So from 1960 to 1990, it looks like there was essentially no change in performance either. Not just that they looked the same, but in fact, many things about them were quite similar. We'll come back to this in just a moment. Boeing is very proud to tout the increasing efficiency of their jet transports in recent years. Here's a picture of the Boeing 787, which compared to the previous generation of airplanes, such as the 767, has about 20% fuel savings and about an 8% better specific fuel consumption, which specific fuel consumption means the is really related to the engine efficiency. So the engines are roughly 8% more efficient than they were on the 767. So here's where we are right now. And we're going, well, or here's a very broad brush look at where we are. But we want to see, we know that things are changing now in the airline industry, in the commercial airplane business, et cetera. And so we're going to first look at why this is not going to maintain a stagnant situation with respect to performance and commercial utility. So I'm going to talk with you today about these three areas, talking about current crises in air transportation. That's where we'll start. And I'm going to talk about safety, economics, and health. Then I'm also going to talk about some environmental issues that are being addressed and need to be addressed. Here is a picture of an airplane in 2020 from CNN. And here you see people wearing masks, but packed into this airplane. This has become a very important thing for the airplane companies to focus on, how it is that you can modify the airplane so that people are not in such close quarters and packed in, how you can modify the airplane so the filtration system is dramatically better, how you can not modify the airplane, but the way you manage the airplane so people getting into the airplane don't have to brush by each other. And so Airbus and Boeing are working very hard at some very new ideas for making these things safer because they can't afford not to. We get some idea of this by looking at the Bureau of Transportation Statistics data. And this data comes from September 8th, so about 10 days ago, 9 days ago. And what it shows is the change in this month, so on the left-hand side, July, between July 2019 and July 2018. This would be 0% change for November 2019 compared to November 2018. When we get to the year 2000, here's January. January actually 2020 was 6% higher than January 2019. February was 7% higher, and everyone was quite excited about that. But come March, the number of passengers flying in US airlines was down 51% from 2019 in March. So that made everyone sit up and pay attention. In April, it really was striking. April was down 96% from April of 2019, and it has continued. So May is 90% lower than May of last year. June was 80%. July was still 73%, and maybe a little bit more. It's hard to say right now because that data is still coming in. But this is pretty dramatic for airlines that are used to very steady growth. And so something really has to be done. So this is one of the things that's creating a crisis, a dramatic drop in commercial air travel caused by COVID-19, and a drop in people's confidence in commercial flight safety associated with the pandemic, but also associated with things such as the 737 MAX incidents and several other things that have occurred over the last year or two. So Boeing likes to also show how efficient their aircraft are, for good reason. Back in the 1960s, when those 707s were flying, they were using early jet engines, and compared with the engines in the 767 kind of second generation jet engine timeframe, they used 70% more fuel per seat kilometer. So a huge amount of fuel being used in the early days. These first generations of modern high bypass ratio engines used on the, or bypass ratio engines anyway, used on the 727 did definitely somewhat better. 767 was better yet. We saw that the 787 used engines that were about 8% better than the 767 engines. And other improvements were made along the way so that relative fuel use combines the engine improvements with aerodynamics and structures. 787 has a great deal of composite structures, carbon fiber, et cetera, on it. And so that all combined leads to a very substantial reduction from Boeing's early airplanes to their current airplanes. They also like to show statistics like this, which are interesting, and they're absolutely right. If you fly from Seattle to Washington, D.C. On a 737-800, and the number of passengers here is an 80% of the maximum number that can fit on it, which is not a terribly uncommon load factor ratio of actual number of passengers to number of seats. But with those assumptions, that airplane can fly from Seattle to Washington, D.C. And if you take the total fuel required for the airplane and the total number of passengers on that airplane, that translates to 29 gallons per passenger to go from Seattle to DC, which is a whole lot less than a car. This is 81 passenger miles per gallon. A typical car in the San Francisco Bay Area, if you said it gets 25 miles per gallon, and actually the statistics say that that the load factor or the number of passengers on average is about 1.3 passengers per car in the Bay Area. That's only 32 passenger miles per gallon, and that's similar to Amtrak, by the way. However, that's the good side of the story. The other side of the story is that, and that contributes to the crisis we're having with, one of the crises in air transportation. Transportation in general is responsible for about 13 to 20% of all greenhouse gas emissions. Aviation is about 13% of that. So 13% times something between 13 and 20% sounds like 2% to 3% of CO2. But the net effect is actually 2 to 4 times that amount, and is increasing. It's increasing, or it has been increasing until April of this year. It's increasing because the number of passengers is increasing, the number of airplanes is going up, and the load factor is not changing dramatically. So from the IPCC report, aviation is about 13% of CO2 emissions globally in CO2 emissions in the transport arena. So aviation is about 13%. Road transport is something like 74%. So it is considerably higher. But that's not a tiny number, especially if you see that this is just CO2, but the contribution to global warming is probably 2 to 4 times as much as the CO2 output for aviation anyway. So this has been concerning people for the last, well, depending on the person, 20 years, 10 years, whatever. And it's gotten to the point where both public and political pressure is really mounting on the impact of airplanes on the atmosphere. So here's a quote from CNN and Friends of the Earth. Air travel is the world's fastest growing source of greenhouse gases. And it is the case that each long distance flight of the 747 adds approximately 400 tons of CO2 to the atmosphere. So here are some scary quotes to people involved in aviation and probably to anyone. Flying kills, we know it, and we all do it, and we won't stop doing it until the government reverses its policy and starts closing the runways, from the London Guardian. This one, it may well be true. Of all the things which an ordinary person does, which damage the planet, flying is far the worst. And I'll just read the last one. Every time someone dies as a result of floods in Bangladesh, an airline executive should be dragged out of his office and drowned. That was in the Guardian. But things have continued to get very problematic for transportation because of the impact of airplanes on the environment. It's gotten to the point, of course, that there is, this article says, flight shame, and that flygskam in Swedish, which I do not pronounce correctly, translates to, flight shame in Sweden prompts rail-only travel movement. And here you see people in the train station. It says, planes, trains, and automobiles for Swedish climate activists, only the trains will do. Which, it's not clear that trains are great, but airplanes could definitely be better. So, the next topic I'm going to cover is sustainable commercial aviation. How could we take airplanes that that cause such problems for the environment and design them in such a way that they don't just make the most money, but also have some significant constraints on the environmental effects. So what I call sustainable commercial aviation includes designing for sustainability, and that involves some new concepts as well. So let me talk about that. So you remember that one of those plots showed the lift to drag ratio, well, actually lift to drag ratio times Mach number of airplanes throughout many years. if you translated that 15 to 17 number of the Mach times lift to drag ratio to just the lift to drag ratio, all of those airplanes flew at very nearly the same Mach number. The 787 flies a little faster than some of the earlier airplanes, the smaller airplanes. And but we can look at other transportation modes. Since the reason you need propulsion, if you are not accelerating but going at a constant speed, and not climbing, changing altitude, is to overcome the drag force. So this is why lift to drag ratio is an important aerodynamic performance parameter. So here's a passenger car. This is some BMW, and it has a lift to drag ratio. Its lift comes from the reaction of the tires on the road, the vertical component, and the drag is also due to some rolling resistance as well as the aerodynamic drag. And if you work out the numbers for this particular car, you get that at zero speed or very nearly zero speed, the lift to drag ratio is about 100 to 1, which is good, but the car isn't doing anything, so it's not so good. At 60 miles an hour, it gets a lift to drag ratio of 40, which is good, but it's only going 60 miles an hour compared to the several hundred miles an hour of those airplanes. At 120 miles an hour, which is still close to takeoff speeds of some of those airplanes, the lift to drag ratio of this BMW is about 16 to 1, which is not as good as some of those airplanes. So from a fundamental standpoint, what the engines have to overcome besides all those ancillary things like friction and the air conditioner, et cetera, is the drag. And so passenger cars are definitely not, especially for the speed, fundamentally more efficient. Ships can be, if they go very slowly, they're like the car, that they have low drag, but they don't accomplish what they're trying to do. I found data on a 550-foot destroyer at 35 knots, and the article said it had it gave the drag of that and the horsepower required to make it go 35 knots. And that translates to a lift to drag ratio of 18 to 1, which is pretty similar to the airplanes. But of course, lift to drag ratio is not the only metric that's important. Speed is very important. That's why airplanes cost more to travel on than kayaks. But the question is, like, if everything is about 15 to 20 for L over D, is there anything you can do to the airplanes to change that, or is that a fundamental physical phenomena? Here's a sailplane called the Eta, and it has a 31-meter span, which is amazingly large, quite a bit bigger than a DC-9. The lift to drag ratio is 70 to 1 at soaring speeds, which is not super fast, but is faster than anything with that L over D that we have seen data on. So it's quite something. Now, actually, steel on steel has very low drag, and so it is quite possible that fundamentally trains could be more efficient. Whether they are in getting from one place to the other is another question. Current transport airplane fuel consumption is partly due to the turbulent fuselage and wing, but also due to the fact that people aren't optimizing for minimum environmental impact. And so what people do in designing airplanes is to model the performance, the airplane performance in general, how long it takes, how long a runway it requires to take off, some of the stability and control requirements. People estimate the weight of the airplane before it's ever built. They estimate the aerodynamics, the noise, the engine performance, and even the economics, and combine this with numerical optimization to try to get the best airplane, whatever that means. So by doing that, one really has to think about many different things. While cost is seemingly a bottom line, there are many constraints that go with airplanes. And so one of them is the economics. And so you don't want to design an airplane where the seat spacing is as shown in this slide. There was a discussion among British low-cost airlines about replacing the seats in their conventional airplanes with seats that were this close together. And so there you were partially standing during the flight. That definitely would reduce some of the costs, but probably also reduce some of the people who would take your flight. There are also environmental constraints, and passengers, as again, need to be comfortable in the airplane, and there are a bunch of constraints associated with regulations that require that you be able to get out of the airplane on the ground in a certain time. And so all of these things have to be shown to satisfy the relevant regulations. We saw a little bit that the optimization included a bunch of environmental constraints, but those are actually very difficult to try to model. And so here, for example, we hear a lot about CO2 and how it affects the warming of the atmosphere. But this is a plot of the relative greenhouse effect, starting, this is indexed to something that is not terribly important, but it's a function of the altitude that the airplane flies at, and it's a function of the emission gas that you're talking about. So at 5 kilometers, so let's see, like 5 kilometers would be 5,000 meters, 18,000 feet. We have the jet fuel, and mostly though, the CO2 being an issue. As we go higher, here we're at 9 kilometers, not quite twice this. And the jet fuel is a bigger effect on the radiation, net radiation into the atmosphere than CO2. I mean, it is bigger than it was down at 5 kilometers, still less than CO2. As we go up very high in altitude though, here now the jet fuel is more important than the CO2. we see with hydrogen, there is water vapor in all of these things produced. But at really high altitudes, the water vapor turns out to be a very important greenhouse gas. So this is, once again, each of these have two lines on them. One for airplanes powered by kerosene, normal jet fuel, and one if you switch to hydrogen. And here, if you're burning the hydrogen, you produce water vapor at an altitude that's in the stratosphere, and it stays there for a very long time. And it turns out that water vapor is a very significant greenhouse gas. It's not so important down at low altitudes because you are below the stratosphere and there's a lot of mixing that goes on, so it becomes rain and gets washed out of the atmosphere. But model this very carefully in order to be able to do the optimization, which a student of mine did and which people at the major airplane companies now do. But she did this for her PhD thesis, and it was very interesting. What she did, first of all, was to minimize cost. And she varied not only the flight path and the kinds of engines and the size of the engines, but also the airplane geometry, different wing sizes, different thicknesses, all of these things. There were many dozens, in some cases hundreds of variables that were changed in order to produce a so-called optimum airplane if you were minimizing the cost. And what this shows is the minimum cost airplane that came out of this numerical study. And it shows the relative cost, fuel, NOx, and overall global warming parameter, which we and folks from MIT put together to measure the temperature increase after a certain period of time. And so these are all one because that's the reference. So then she said, okay, let's just minimize fuel. And the fuel is only 82% of what it was for the minimum cost airplane. The cost was a little bit higher. NOx was a lot lower because there was less fuel. And the global warming parameter went down. Then she minimized NOx, which turned out to cost a lot and to require more fuel. And the global warming metric was about the same as the minimum cost airplane. And finally, she looked at minimizing the global warming over 100 years without regard to cost, fuel, or NOx emissions. And the cost was higher, but looks like about 11% in this case when she ignored the cost. Fuel was lower, NOx was quite a bit lower, and the global warming parameter here was down to only 20-some% of what the minimum cost airplane was. So that's very interesting. She went on to do a specific trade between cost and climate. This is called a multi-objective optimization. And here was the reference airplane with a cost of about 1, flying with the 100-year global warming included reference to this same initial airplane. Whoops, get to that. So this was the reference case with very little change in cost. The global warming came down. If you changed a number of things on the airplane, she didn't draw this particular point, the airplane shape. But as we started emphasizing global warming more and cost less, each of these points represents the lowest cost airplane for a given global warming, or the lowest global warming for a given cost doesn't work. The lowest global warming for a cost not greater than this is not even it. So for a particular cost, this would be the lowest global warming values. You might have airplanes out here which you wouldn't be interested in. So these numbers are the altitudes in thousands of feet where these airplanes are flying. She also optimized for every airplane the cruise altitudes, as well as the cruise Mach number. So what happened here is that the airplanes came down a great deal in altitude, slowed down a little bit. So this one's at Mach 0.77 compared to 0.85 up here. And that's what's mostly responsible for the increase in cost. But the increase in cost, including all of the factors that go into total operating cost for the airplane, is only less than 1% higher than the reference airplane. And it's very steep in here. So you gain a huge amount in this global warming metric. With even out to here, you're only 30% of the global warming metric, and you're only 2.2% of the cost. So that's interesting. If you keep going and say cost doesn't matter, you get an airplane that looks like this. And it has, it's pretty flat in here, so it doesn't make sense to go quite this far, or maybe even quite this far, but the cost is 12% higher. And no matter what the environmental goodness was here, it would undoubtedly not be worth there. So there's a 12% increase in cost, and the airline margins when they were doing well were less than 5%. So this would definitely be a problem. But still, this idea of that you could come down a little bit in altitude and a little bit in speed and have a substantial change in the environmental impact was a real eye-opener there. Well, in addition to optimizing these parameters, you could think of new ideas for what the airplanes might incorporate. That's what happens when you run the optimization, but you can also change the configuration assumptions. So in this particular case, this was a study that Boeing did rather recently, looking at using struts to enable a much larger wingspan. You noticed on those optimum airplanes that Emily drew, the spans were going up quite a bit. So this is sometimes called a strut-braced wing, but it was a program that Boeing did optimization on and did a lot of studies on for NASA. And this is partially electric, partially conventional engine technology. Here's another study by Airbus, and this is a pretty different looking configuration. It has horizontal tail for noise reduction, very high bypass ratio engines. People might call those ducted fans. Very large span again. If you look closely, you can see it also has a strut, but a much less significant strut. Finally, you could really make dramatic changes to the configuration. And here's an example of that. This is a Boeing design as rendered by a very good firm in Canada. This fictitious airplane on the runway in front of a fictitious city. So it's amazing how realistic that looks. Okay. So with that, I am getting ready to talk about the last part of the discussion here, reinventing air transportation. I thought actually, both because it's pretty easy to get zoomed out on these things, get tired of sitting there looking at a screen, I thought we might have some questions and do this more interactively for a few minutes. Luann, do you have anything?
Hi, everyone. My name is Luann. I'm actually the community manager of Hannah House. So I've been monitoring the incoming questions. And so we do have a couple that seem like a really good questions for Professor Kroo here. Let me start with this one. It says, aside from energy density of present day batteries, what are some other technological challenges that need to be solved to allow for electric propulsion to exist in mainstream aircraft?
So that's a very good question, but if you looked at that outline slide, you would see that that's the next topic. So thinking about what is necessary for electric propulsion and what people are doing. This relates to fuels in general, but particularly electric propulsion. So we'll talk about energy storage and batteries, as well as the related issues with electric propulsion. And we'll talk about its application to small, not so small, and regional airliners.
Okay, great. Looking forward to that. So another question is, do you foresee drones being controlled by central authority, autonomous under individual authority, or by an operator, especially in crowded suburbs?
Yeah, that's also a good question. There's been a lot of work at places such as NASA Ames Research Center on just that kind of thing. And as autonomous airplanes become more widely used, many people are looking at various approaches to this. So all those three versions of control that you mentioned are all things that have been considered, and some of the companies are pursuing each of them. At the moment, it looks as though some combination of autonomy with some kind of backup ground controller, who you don't have to have one ground controller for each autonomous airplane necessarily, because most of the time the autonomous airplanes will be doing fine themselves. But some kind of ground-based system in the event of an emergency. And that combined with what is needed right now are some improved rules for operation of autonomous aircraft, for doing things other than just being model airplanes.
But actually, just wait.
Okay.
So there are companies. There is one well-known company in Slovenia that has been building electric airplanes for quite some time. And they have just announced a autonomous cargo delivery vehicle, which, unlike some of the small UAVs that deliver medical supplies, this one is going to go between transportation, or rather distribution centers, taking large amounts of goods. So this takes off from an airport or some place. It's a pretty heavy airplane, and it can carry a lot of stuff. So if you Google Pipistrel, that's the name of the company, you will undoubtedly see pictures of their new cargo UAV. So all of these, none of these things is yet in place to really make this a acceptable set of airplanes to fly along with commercial airplanes. So there's a lot of work to be done in defining not only the sensors, but also the way to communicate with the airplanes, to be able to know for certain where they are, and many applications of ADS-B, many things the FAA is working on, as well as the places like NASA.
Okay, and another question is there a danger of planes on fly-by-wire being hijacked or otherwise interfered with remotely? If so, what safeguards could be implemented?
Yeah, this is a whole field of research, not just for being flown wirelessly, but even the sensors themselves. So a big issue is how to ensure that accurate location, that the airplanes know their accurate location, and that the people on the ground know that. And so building GPS systems, which are much more reliable, harder to jam, and harder to spoof, is a big field in GPS research right now. Many other sensors are super important for airplanes. Those also have to be very reliable and robust. So this is an evolving area, but it's not just the communications part. It's many different things about the airplanes.
Okay, and did you have time for one more question?
I think so.
Okay.
When we're wrapping up by 6:20-ish?
6:30. 6:20, 6:30.
Mm-hmm.
So okay, so it says here, how many years away do you think we are from electric vertical takeoff and landing crafts being deployed in urban settings? Which countries' markets do you foresee the first commercial deployments? And what are some of the biggest challenges to get to commercial deployment?
Okay, Luann, if you could ask me this in just a little bit. This also is specifically covered in the last section of my talk. So
great.
Probably won't answer all those questions, but remind me of them and I'll get to each one of those at the end of the talk.
Okay, great. Okay, then let's move forward with your presentation then.
Okay, so this last area is associated with doing pretty dramatic things to our air transportation system. And that's why I call it reinventing air transportation. It will deal with electric propulsion and how that might be used in regional or sub-regional. Sub-regional is a term that's mostly used in Europe right now, but we'll probably hear more of that. That is shorter range commercial airplane flights. Advanced air mobility was for quite some time called air mobility by Uber and several other people doing vertical takeoff airplanes. It's now called advanced air mobility because it doesn't necessarily mean vertical takeoff, as we'll see. And the idea here is to turn this flight shaming, flight shame into flight pleasure, which is apparently the Swedish word that's pretty much the opposite of that. So let's see what we're talking about here. So one thing that people have looked at a lot is looking at alternative fuels. Not just alternatives to Jet A, which is the usual fuel used in large transport airplanes, but also synthetic jet fuel. And as you've undoubtedly heard, several airlines are experimenting with synthetic jet fuel and even biojet fuel, which is made from organic materials. What this part of the slide shows, and sorry, I didn't make this slide, but I found it. It shows how Jet A does relative to some other fuels. It's pretty much the same as synthetic jet fuel or biojet fuel. But if you were to use ethanol, for example, for a jet fuel, that would require 60% more volume than Jet A. And if you were to use liquid hydrogen, it would require 400 or 320% more, or actually 4.2 times as much volume as Jet A. And so that's a bit of a problem because the fuel is generally stored in the wings of commercial airplanes and some fuselage tanks, but it can be an issue, especially if you need 4 times as much volume to store the fuel. But maybe to a greater extent than cars, for which there are liquid, or there are hydrogen, gas hydrogen fueled cars. They do, volume is important there, and their ranges aren't what they might be with in some other situations. But you might also look at the weight. So for the same amount of energy, for the same weight, you for the same energy, you get only 36% the weight if you're using liquid hydrogen. Jet A is again normalized to 1, and ethanol has more weight for a given energy level. So you have to look at all of these considerations and all of the other things that aren't listed on this slide that are important possible things to use for fuel for an airplane. And you have to look not just at energy and volume and weight, but specific power too. How much power can a system generate per unit mass, for example? So on the vertical axis here, we have watts per kilogram of specific power. So we see that combustion engines are really high up here, but to produce a certain amount of power per unit mass. Whereas here's some batteries. Here's a dry cell, which produces a range of specific powers depending on its geometry and chemistry, etc. On the horizontal axis is the specific energy, and by specific power or energy, we mean the particular amount of power or energy per unit mass. So specific energy is measured in watt hours per kilogram. A Tesla's batteries are about 200 and something, maybe 240 at the cell level, watt hours per kilogram. So that's kind of at this point on the horizontal axis. They're also pretty decent at specific power. But as you can see, combustion engines go up to much higher specific energies. And it's not just the engine in here, but it's some amount of a kilogram of fuel. Well, not quite. It's the combination of fuel and the engine itself. Fuel cells similarly can be pretty good in energy, but have much lower specific powers. So that can be a problem. Here we have a number of different chemistries that could be used for storing energy in some way. Batteries are very interesting. As I said, the lithium polymer or lithium ion batteries used in a Tesla are something over 200, and it depends again whether you're talking about the cell level or the complete battery level, and those can be different by more than 20%. That is, you can have to multiply the watt hours per kilogram by 0.7 or 0.8 to get the battery level values from the cell levels. Anyway, there's a lot of battery research going on. This one is by a company called Amprius that I think is located in Saratoga. It's not very far away anyway. And it replaces the anode with that might be used in conventional batteries with silicon nanowire. And it actually has gotten up to about 400 plus watt hours per kilogram. So this number strikes people as being super important because it really makes many electric airplanes viable if you have substantially less than this, like half of it, which is still a pretty good battery. You have a very limited range or time in the air, etc. Airbus is actually using these batteries for a high altitude, long endurance airplane called the Zephyr. It's sometimes in Europe, it's sometimes called a HAPS airplane, high altitude pseudo satellite, because it stays in the air it has stayed in the air for a month. And it has solar cells to charge the batteries. And then at night, when there's little solar radiation, it discharges the batteries. So the batteries have to have a decent cycle life. The airplane has to be very efficient. These things can fly at 50, 70,000 feet or even higher. And there aren't very many of them, but this is probably the most recent success that's actually going to be used for some things that satellites could be used for. But in some senses, better than satellites, because if what you're doing with them is transmitting cell phone information, cell phone data, or other high bandwidth data to Earth, it's better to be 10 miles away from the ground than 200, 300 miles away from the ground. And if something goes wrong, you just land them and put up another one, which is hard to do with some satellites. So Professor Yi Q is, it's not how you say it properly in Chinese, but it's how it looks. He's a professor at Stanford. He founded this company, and he is running a series of seminars that I thought some of you might be interested in. And so here talks about battery research from academic breakthroughs to technological impact. Stanford Energy's work in this area is called Storage X. And there are material scientists, there are computer scientists, there are economists looking exactly at this question of energy storage, electrical energy storage. I've been to many of these seminars and they're often really good. This particular one is tomorrow, and they try to allow people from Europe to parts of Asia to zoom into them. So it starts here in Pacific time at 7 a.m. And you can find out about this by going to the Stanford website and just Googling Storage X. So that would be interesting. So if in fact Storage X or Amprius or many of the other companies that are working very hard on battery improvements succeed, many things will be possible. And this is pretty timely, I think, but also here's a concept that was just announced about a month ago, a little more than a month ago, which is a interesting design. It's a hybrid electric regional aircraft. It carries about 70 passengers, which makes it very large for an electric airplane. But it's it is something that the engines and batteries of today are compatible with. This is from a company, as you see, called EAG. And EAG expects that its first version of this will be in service by 2028. So not too distant future. It's still pretty nearly impossible to get this to work with batteries of even that are likely to be around by 2028. So you can see here that here's a bigger engine than this one. And so that's why it's called a hybrid electric propulsion system. It's going to use the more conventional turboprop engines that burn some kind of fuel. They haven't said exactly what it was. And one of the things it can do is allow you to use electric propulsion on takeoff and landing, where noise is very important and emissions are very important too. And then when you're cruising along at reduced throttle settings, the engines that burn the fuel can actually recharge the batteries that run the electric motors, which is a cute idea. So we'll see. Most people would be quite skeptical you can put together a 70-passenger airplane that runs on a substantial amount of electric power. We'll see. That'll be fun. You can, of course, make smaller airplanes that can be powered with current batteries. And this is Airbus's EFAN concept, which was really a researchy development thing to learn more about electric motors and batteries. But you could imagine that these things could be flown around and be very quiet and not have any emissions from the airplane to speak of, and be also quite good in terms of maintenance. So there are many reasons that people are looking at small electric airplanes, and small because the battery energy just scales better at small sizes where you don't need quite so much power, quite so much energy for a given time. So here is a picture that I don't actually know where it was taken, but it's scary wherever it was taken. So if we can fly electrically, let me just see something here. We could fly in some of those airplanes and take off from some place like Palo Alto or San Carlos and fly to somewhere south of San Jose, Monterey. And they don't require San Francisco International because they are small, lightweight, and low takeoff speed airplanes compared to usual commercial airplanes. And if we can do that and it is reasonably economical, we could avoid this, which is definitely not reasonably economical by any measure. So this is one thing that has excited people, not only for traveling the way most people do in today's commercial airplanes, but being able to get around for regional distances from city to city, or even from one part of the city to a much more distant part of the city. And I'll say more about that in a minute. But if you could do that, it would save people an awful lot of time. So there are now many companies that are looking at ways to possibly do that. This is a pretty new company called Electra.aero, and they are looking, these are mostly folks from MIT and other people who have been in the airplane business. This is an eSTOL, an electric short takeoff and landing airplane. So it is made to be very efficient. It is all electric. This is just an artist concept. So they're working on figuring out just how feasible it is. But the idea is to land on a very short runway. So it could even be this platform out on a river here. And this looks like New York. But in any case, the idea is that this would hold a few passengers, maybe from 4 to 9, but this airplane is right now just a design concept. But it could be very interesting because you don't always have to be flying in an airplane that can go 2,500 nautical miles. So you could do this, which would be very interesting. And I'm quite interested in variants of this, which are maybe less complicated, but still might serve the same group of people who want to travel and be very clean and efficient. Some of these things started with the idea of personal air mobility, and this was a design by Mark Moore from NASA at the time. He is now with Uber Elevate. And Mark made some great videos of this airplane, which is, as you can probably tell, just a rendering, but could be a very lightweight, simple, low energy way to travel at reasonably high speeds, just for one. Now, some of the companies in Mountain View have actually built some airplanes and flown those airplanes a lot that would carry one person and be able to take off vertically as well. So there is a lot of interest in this area too. Of course, you could just do something like this. Was in the very early days of people trying to do this. These look like model airplane motors, and you need lots of them and lots of propellers, not only just to get the thrust needed to take off, but also to be reasonably robust to failures. So this was, I don't know the exact date, but relative to some other things that I remember, it was probably 8 to 10 years ago. So early days of electric vertical takeoff and landing airplanes. This actually became the German Volocopter. And here you see a picture of it many years later. This picture is taken in 2016, and it is flying with the same large number of rotors, again, probably for redundancy, and a much more reasonable looking fuselage. I mention this because there was an announcement today on Volocopter, and they published this picture. It has some very sophisticated control systems. They have been flying for quite a while, and it looks interesting. But the announcement today was that you can buy a ticket. You can reserve a ticket anyway. And they're selling 1,000 of these tickets, and you just go to eventbrite.com. Or you can also just Google Volocopter, and it's becoming a lot more believable when some of these folks are EHang is flying tourists around for sightseeing in China, and people are delivering medical supplies and all kinds of interesting things. So that is that's an interesting, nicely put together eVTOL, along with some others. Another eVTOL here is from Joby Aviation, which combines wings of an airplane with propellers and rotors to fly efficiently at higher speeds than the Volocopter probably could. And Joby has a good deal of funding and has quite a few people from this area. Lives in the Santa Cruz Mountains and has done some really cool work. In addition to designing some very nice camera tripods. That's another story. Here's a similar configuration that flew quite some time ago, in this case, autonomously. And here is the Z Aero configuration, which was a prototype for a bunch of other things that followed. But this was an airplane that was weighed somewhere between 600 and 800 pounds. We at Z Aero at the time built the motors for it, the flight control system, and even most of the structure at one point. But just to show you what this does, let's see if this works. So we were down at Edwards Air Force Base, now Armstrong, NASA Armstrong, and basically put this out on the runway there and hit the perform flight test button. And it did this entire flight test by itself with no input from the ground. So you can see it taking off vertically. It has 8 vertical lift fans and 2 pusher propellers. It wasn't terribly noisy on takeoff. And then what we did is to turn on the pusher propellers and throttle back to nothing the lift rotors. And there you see it accelerating. And by this time, as it went by, some of the rotors were just windmilling there. In real life, we would lock them in a low drag position. But it was almost silent. You really couldn't hear it at all. And so it flew past and then was pre-programmed to stop before the end of the runway. This was a very long flight test runway for both NASA and the Air Force. So flew by, entirely supported by the wing and canard lift. And then it was programmed to stop at that point, Mark 1, and to descend and to land entirely on its own. Has lots of sensors to know how high it is, lots of redundancies, so that if anything fails, it wouldn't be a problem. And there it lands nicely. So this was just, we were very happy about the first completely autonomous flight of the airplane and VTOL and forward flight modes with transition. Whoops. So all of these things have spawned a number of companies to move forward on interesting variants of these things. Uber Elevate was one of the early companies to propose not just airplanes, but a whole infrastructure to support them. And the group that is doing this within Uber is now called Uber Elevate, and they're doing a lot of very interesting work I can give you some context if you are interested. But this is, for example, a building with a so-called vertiport on it, where these airplanes can take off, fly to another vertiport in the city, land there, or land at an airport near the city and take an Uber ground vehicle to where they want to go. So lots of possibilities there. Here is, just to show you real quick here is a small eVTOL personal aircraft developed by Airbus. And many of the people on this particular team were former Z-Aero Kitty Hawk people. Here is the current Kitty Hawk airplane called Cora. And it was featured just a few weeks ago on the cover of Aviation Week. And you can see all kinds of interesting things if you look hard at that. Okay, so I'm going to try to wrap things up a bit here and say there are all kinds of technologies and research areas that require work, from propulsion to vehicle autonomy to machine learning to scalable structures and design methodologies. So it's a great thing to do if you're also a professor at Stanford, lots of projects to work on. And so in conclusion, we have a class on autonomous aircraft, in fact, and the fellow who is throwing this airplane over Lake Lagunita now works for Uber, and this is a great area for students to go to work in. In this course, we do all kinds of things from solar power to urban air mobility to search and rescue with autonomous vehicles. And just to wrap up, it does appear that air transportation, revived and reinvented, has a very exciting future. And I'm very much looking forward to see how things evolve. Thank you very much. I will answer any questions we have time for.
Okay, so there's just one clarification question. Based on the costs you've had in your charts, what does that include? Cost of development or cost of operation for the airlines?
So there were probably a couple of charts which had costs on them, but in the case of the commercial airplanes, like on this slide, these are total operating costs for the airline. So this includes the costs of the pilots and the maintenance and the fuel and a variety of other things, but it is directly related to the price that a passenger would have to pay, but it's normalized here.
Okay, great. Thank you so much. So, all right, I think we're getting ready to wrap up here. So everyone, thank you for tuning into our our Café Sci this evening. And thank you, Professor Kroo, for taking the time to speak with us about this topic.
It was my pleasure. If I could say that, please feel free, anyone in the audience who does have more questions, to contact me at this email address. I'd be happy to answer questions.
Thank you. And also to the audience, we hope to see you all for next month in our last Café Sci event of the year. And a lot of you were asking whether we will have a recording of this, and we should have it on our Hannah House YouTube channel in the next few days. So look forward to that. And thank you again, everyone, for joining us, and hope you have a good rest of your Thursday evening.
And thank you from me too. It was fun to do.